So I think we can get started now. So I'll be presenting the 2-hour workshop on Julia, interactive computing on Pitt's Daint. For those who just joined, I think if you haven't already set up your or reserved your node on Jupyter Lab, the way to go is to go to jupyter.css.ch. And I'm already logged in, but if you go there, then probably you have to click start my server on a probably single node GPU partition. If you want to follow along, you might want to get the notebooks that I have here, and they're part of this repository on GitHub. So I think we could share the link. Okay, I think Tim can do this for me to copy and paste the link with the notebooks. And if you happen to have gotten your node on Jupyter, then one of the things you may want to do is to hit the plus button, go to terminal, and it will give you this amazing terminal where I already did it here. I ran this git clone and then the repository, and I did this in my home folder, and then it should be available on the left-hand side. So I give you a second to set that up, and then we should be ready to go. Okay, so I have presented or I've prepared a couple of notebooks that I'm going to go through. This morning I woke up to the noise of construction work at the next block, so I'm improvising a little bit. When I opened my window this morning, the first thing I saw was somebody throwing a bathtub out of the second floor of the next building, and there is quite some noise. So I tried this thing where I switched to Windows and used some noise cancellation in the microphone, and I'm very much in an out of my comfort zone here, but if everything works, that's probably a good argument for Jupyter because it should work from anywhere. So let's get started. The Julia talk was anticipated, at least by some of my colleagues at CSCS itself. So I hope I can live up to the expectations that they have. I think there is quite a mixed audience. So at CSCS, we'll have people who are used to writing C++ and maybe do low-level optimizations in there. We have people writing Python interfaces to C++ code, all sorts of things. There might also be people who just use Python and Jupyter and do visualizations. I hope for anybody there is something to take away here. As Tim mentioned in the introductory talk, Jupyter actually stands for, or has the Ju in Jupyter is for Julia, the Py for Python, and probably the Tur for R. It is it is around for almost a decade now. So people think that Jupyter is kind of the new kid on the block, and I guess, well, it's kind of new still because there are languages that are much older. It has a stable release, the 1.0 release, released a couple of years ago, and currently we're already at version 1.6 that was released not too long ago, and Pitt's Daint also upgraded the Julia release. I get the impression that Julia at this point is rather stable in the sense that it's not rapidly changing, and particularly in the 1.6 release, if you go through the release notes, you won't see any drastic changes to the language. It's more polishing work to make it easier for users to get started with it. And my goal of the notebooks is not necessarily to convince you that you should be writing only Julia the entirety of your life, but rather that it certainly has its place in high performance computing. It allows you to quickly prototype and without losing performance, which you might sometimes have in the Python world, where you have to switch to C++ and do some hybrid development. In this presentation, I won't be talking that much about distributed computing. I'm rather just doing like single node stuff. If you're interested in that kind of thing, then Samuel Omlin, who is also at CSCS, wrote a Julia package, Implicit Global Grid, and he presented it at the Julia conference this year. There is a video for that, and I think it should be rather good. I mean, go check that out. It's more about like using a bunch of GPUs and Julia with MPI. What I will be talking about is rather Julia's language features, and I'm going to show you like rather playful examples, like how you can do both CPU and GPU programming interactively, and I encourage you to follow along, just try it out. So assuming that you have managed to get the notebooks, just to be sure that it actually, as a sanity test, it actually does its thing. I have these couple cells. A couple of things you can see is that Julia has types for different types for integers and floating points. Clearly, this is not an equality in floating point arithmetic, but 0.1 plus 0.2 is approximately equal to 0.3, already showing off one fun Julia thing. Julia comes with a bunch of built-in standard libraries, and you have to import them into your scope by writing using and then the library. So one library that you might be interested in is, for instance, the linear algebra library. If you do using linear algebra, it will import some of the things that library exports, so such as the diagonal matrix type. And already when I'm doing this, you can see that it has some pretty printing for the matrix, but it also shows that it is a diagonal type. It has element type integers, and the vector that actually creates this diagonal matrix is some unit range. Then you might, I don't know, you might want to figure out some properties of this matrix, like what are the eigenvalues. And also already there you see one neat thing about Julia. It recognizes that you're asking for the eigenvalues of a diagonal matrix, so it immediately returns the diagonal itself, which seems to be the correct thing. More standard things are the dense arrays. There's again some funny features where the I is part of the linear algebra library, and this is a short way to write 5 times I, and you get a dense matrix, which is like random numbers plus 5i on the, like a 5 on the diagonal.
Sorry, just to interrupt just quickly. Can you increase the font size a little bit?
Yeah, sorry.
Thanks. That's better. Thank you.
Great. All right. So if you look at this guy, you might see it's a matrix type. In fact, it's just an alias for n-dimensional arrays, which have proper support in Julia out of the box. So the matrix is actually just a two-dimensional, the 2 here is for the dimension, array of floating point 64 numbers. And then you might call this eigenval function again on B, and you get a bunch of eigenvalues. There's some pattern in here. So turns out that if you generate a random matrix like this, its expected value is exactly this matrix. It's a bunch of numbers 0.5 with 5i on the diagonal. So the eigenvalue should be some kind of a perturbation of this guy here. And it also comes with sparse arrays out of the box. So if I'm running this here, it's kind of like MATLAB in a sense, or maybe NumPy or whatever. It pre-prints the sparse matrix, the structure of it, in this Braille Unicode character font, and so that also the blind people can read the structure of the matrix. You can do arithmetic with it, so like some linear algebra, like I can do a sparse matrix times a dense vector, and I get a dense vector out of it. But clearly not everything is implemented in Julia out of the box. So for instance, if I try to get the eigenvalues of the sparse matrix, then it throws a wall of text on me, and it says there is no method for eigenvalues on the sparse matrix. So in that case, you will have to look for packages around on the internet. So I happen to have written a package that actually computes eigenvalues of sparse matrices. And I can add a package like this using the package manager. I can add the package, and then it should be available in my session. And then I can import this function partial sure for those who are into eigenvalues. It's kind of like the Ike's function in MATLAB, if you remember that from back in the days that you used MATLAB. It just computes like a couple of eigen for like a partial decomposition of the matrix instead of a full one using an iterative method. So this is quite nice. It's kind of like MATLAB, except that everything in this package, for instance, is entirely written in Julia, not just the high-level algorithm, but also like the low-level details are written in Julia. And it was like one of my first project where I just wanted to see like, okay, what can I actually do with this language? And there was some push for people like, can we write everything that we know of can we rewrite it in Julia? So I try to do my part and see what I could do. Then you can, I don't know, like see if this is actually like close to an eigenvalue or sure decomposition. Like there's some mathematical equalities that should hold, and it seems to work. So that's a kind of way that you can use Julia interactively, just as to get started with packages and everything. There are many more packages and convenient ways to get them. If you use this square bracket and to add Unicode plots and distributions, it will be like a shorthand to add multiple packages at the same time. So it makes it a little bit more convenient. And then you can start using them. And you get some high fidelity bar plots, for instance, using this Unicode plots package that it's just text that you can copy and send over chat. It's very convenient. Or get a heat map where I'm using all kinds of Julia tricks like broadcasting and well, I'll get into these details later about what this all is, but or I could make a histogram of random numbers taken from a particular normal distribution. And okay, just to get started. In some cases, you might be a bit worried about if you add a bunch of packages that they might explode your home folder on Daint. So you have this convenient file, jupyterhub.env in your home directory where you can set some variables. One other thing you could do is set the Julia depot path to, say, scratch /Julia or whatever, just in case you get download a lot of big things. But for this notebooks, I don't think it was entirely necessary to do that actually. Another thing that's quite important and quite nice about Julia is the package manager is really world-class in the sense that everything will be kind of in a virtual environment. If you're coming from Python, you can just create a folder somewhere and activate an environment in that folder. And the environment consists of two files, a project.toml file. My server is not running. They're run out of, okay, I have to figure out what this is about. So you have a project.toml file, which is a human readable list of packages, of Julia packages by name and some UUID, and a manifest.toml file. It's not human readable, but it's for reproducibility. Basically, if I give you a project.toml and a manifest.toml file, it will be enough to reproduce the exact packages. So clearly, as part of the as part of this set of notebooks, I included those projects and manifest files so that you are guaranteed to get the same packages that I have. The way that works is you just open a notebook, run activate in the current directory, and it will activate the environment. And then I can run instantiate, and it will download all the packages if necessary. If you're interested in knowing like what's actually out there, well, part of my talk will be showing some of the packages, but there's this website called juliahub.com. It has a whole list of them ordered by popularity according to some statistic. And you can check that out if there's anything for you. So enough about packages and everything. What I want to show you first is maybe like what is special about Julia, or what is different from Julia than what you know from Python or C++. One of the things that is kind of interesting to me, at least, is in Julia, functions are first-class citizens, and every function is in a sense a free function, meaning that a function is not owned by an object or not like encapsulated by some object. You won't see like matrix dot multiply and then another matrix. You will only see like multiply matrix and another matrix. And in fact, if you look, for instance, at the plus function in Julia, I think I have to restart my notebook for reasons I don't know.
Maybe just try restarting the kernel to start with, because at the moment you've got no kernel at the top right hand.
Okay.
Just first of all, just try clicking on that and restarting it, because it looks like the server is still running.
Okay, thank you. Let me just run all the cells. Okay. Yeah, it's doing its thing. And let me also, sorry for the interruption. Okay, it's running all the cells. Now it's starting to install packages and whatnot. Yeah, one thing that that might turn you off with Julia every now and then might be that actually running things can be slow at the first time, but I'll talk about it in a sec. So okay, here we are. So we have, for instance, here this plus function and the square root function, and if you just evaluate that in a cell, it will tell you what it is, and it turns out it's a generic function with a bunch of methods. So The thing is that you can extend a function with a method if you want. And you can also see what implementations there are, like what methods are there for a certain function. So for instance, the plus function here has 288 implementations or like methods. And if we just look at the first 10 of them, there is, for instance, just the plus where the argument types are like some integers, and it's defined in the Julia base, like in the Julia source code. Or there are all kinds of other ways to implement plus, like for matrices or whatever. And this is kind of interesting. There is this quote by Bjarne Strostrup, the designer of C++, in an article where he talks about new languages. And he reflects actually back on C++ and talks about the idea of unified function call. And he talks about this difference between x.f of y and f of x and y. And he recognizes actually as a mistake in his design of C++ back in the days, even though it was very fashionable to write stuff like x.f of y. It turns out his issue with it was that it did not really allow for generic programming as much. If you have to differentiate between those x.f of y and f of x and y. And in particular, there is, in many cases, not always like a single most important object to own the function. And in particular, if you're doing mathematics, functions are usually just mappings between spaces. And it doesn't always make sense to make like, you don't do like a 2 dots plus, or in some cases, it doesn't really make sense to make the function to be part of the object itself. And he also talks about allowing virtual arguments for f of x and y and z, and says that it gives us multi-methods. And these are in fact things that are implemented in Julia, so it might be interesting to check that out. This is not yet about high performance computing whatsoever, but I'm just starting with a dummy example where I'm defining my first Julia type myself, an animal, and I'm creating a dog and a cat as subtypes of these, and they have a name. And then I'm implementing a function in Julia, which takes a dog and a cat as an argument, and a dog barks at a cat, and one dog sniffs another dog. And then I could run this function meets, give it a dog and a cat as arguments, and meets will dispatch to this particular function. Or if I give it 2 dogs, it will dispatch to this function there. You might also want to call like, I don't know, meets with 2 cats, and well, it's not implemented, so there's nothing to call, and it will throw a method error. So you don't necessarily need to implement certain things if they don't make any sense in a world where cats don't meet. Sometimes this is useful because you don't have to implement like a full interface to just quickly start prototyping on something. You can take it a step further and do like a triple dispatch. So you would dispatch on the function, but also on 3 different types, like this group interaction function. And here I'm creating a vector, which has 3 animals in it. And you can see that the compiler figures out that the type of this vector must be some vector of animals. And this is where things get a bit interesting, and it shows that Julia is actually a dynamic language. If I would call this group interaction function and then get like random elements from this array, the compiler, just by looking at this statically, it cannot know that the first guy, the first dog, the first animal is in fact a dog, and the second one or the third one is a cat. It just knows like all these guys are animals, and so it has to look up what function to call dynamically. This is something that for the C++ people seemingly makes Julia not very interesting, because it would be very dynamic and slow language if this is all that there was to it. But luckily, this is something you would try to avoid, and there are tools to figure that out that in some cases the compiler cannot get like the concrete types of the things you want to get. So for instance, if we call the function first on vector of animals, it will warn us in red. If we wrap it in this code warn type macro, it will warn us that if we apparently run this function somewhere, there will be some abstract type. And it will cause Julia to be like a dynamic language. Generally though, if all types can be inferred, then Julia, I would say, is not really different from a static language. It's just that the compilation that it does is deferred to the very end at which you actually call the function with particular arguments. So as an example here, I have this function f, generic function with one method, this one. And I'm using these useful macros code typed, and I'm calling f with floating point numbers. And it'll show that the compiler understands that everything in there is like floating point arithmetic. Whereas if I would call it with integers, it will notice that it's integers. And I can also actually look at the native code generation. So there's like the assembly code. If I provide it with floating point numbers, it will specialize on those and generate specialized code using floating point registers. It optimizes a bit, like it doesn't do 2 times, but it adds a number to itself. So that's the add. And then it does a multiplication. Whereas if you would call it with integers, it does some integer magic. So the point being that even though it has only one method, whatever argument types you provided, it will specialize on those, and it will generate code that is optimal for these particular types of arguments. And I added this note, which may be a bit opinionated, but very often you would want to write code in Julia just like this. You don't want to actually add like type annotations. You just want to write like the compiler. The point I'm trying to make is the compiler will optimize depending on the argument types, and you don't have to hint that this is really an integer, the second argument, or whatever. So that's a lot of theory, and it might be more interesting if we actually look at an example. So the point of this example will be that it's very easy to get started in Julia, make your own types, and get Julia to do generic programming in Julia with well, just a couple lines of code. And one interesting example is auto-differentiation. At least it's interesting in the realms of artificial intelligence, and it's this special number type of the form a plus b epsilon, where a and b are real numbers, and epsilon squared is taken to be 0. And the idea behind those numbers is that if you have some function that can be formally expanded in a power series, so for instance, I have f of a plus epsilon, and I would expand it around f of a. I get this power series through like a Taylor series, and you see all those epsilon to the power n's will be 0 because of this useful property. So what it ends up with is in fact another. So this is a dual number where the first component is the function evaluated in a, and the second component is actually the derivative of f and a. So by magic, you get the derivative of a function by just evaluating lifting it into the space of dual numbers and then evaluating it with your a plus epsilon. And then you might want to implement this in Julia, and I'm staying kind of close to the maths, trying to use an epsilon. If you want to, let me just give you a quick example here. If you want to know how to actually type those guys, we hit for epsilon and then a tab, and it will expand to to this epsilon symbol. So I define my dual number. It has the x and epsilon components, and they're both of a type t. That is some kind of real number, and the dual number itself is going to be a number. These are built-in types in Julia's type system. And then I can already create my my first dual number. And to do any useful arithmetic with it, I would have to implement a bunch of functions, but not too many. It's actually just addition, multiplication, etc., to do the basic arithmetic, as well as giving Julia an understanding of how to get from some real number to a dual number, like in arithmetic operations. And I want to pretty print it, which I already accidentally showed here, as well as conversion between types. So I've implemented addition, which is kind of standard, as well as division, which is a bit non-standard, but you have to kind of, given two numbers, you have to simplify this expression, and then what you get is apparently this here. So multiplication, subtraction, also the single argument minus to get like the minus version of a dual number. And conversion and promotion. Well, I'm not going to go into the details of all of this, but conversion is basically given some x, how do I make a dual number out of it? And promotion is more like, given two types I'm doing arithmetic on, what should the resulting type be? So I just wrote like, if you do any arithmetic with a dual number and some other number type, it will always be a dual number. I added a simple constructor and the pre-printing, and now I can already start using it. So here I'm defining a polynomial, and also I computed by hand its derivative. So this is, I think, correct. And then I can evaluate p, the polynomial here, in the point 4.0, but then lift it into this space of dual numbers. And what I get is not only p of 4.0, I'm also getting what should be the derivative, and I can verify it with p prime, and it's indeed the derivative here. Then for simplicity, I created this delta function where it takes some function I want to call, and basically I want to call f of x, but I want to get the dual, like I want to wrap it in a dual number. And then I can apply this function element-wise, and the value is x equals, like on this range of 1 to 10. And then I get out there a vector of dual numbers, and it shows me, so the x value of it shows me p of x as well as p prime of x there. So you might want to actually test if this is anything correct. So you could import the standard test library in Julia. I defined some range of x's between -10 and 10, 100 of them. And then this is my tiny test where this is the core of it. I'm just comparing, like, if I'm evaluating p, but I'm wrapped in x, but I'm wrapped in a dual number, and I take the epsilon part of it, which should be the derivative, is it approximately equal to the true derivative in x? And I'm doing this for a bunch of different x's, and I want all of these to be true. And then I run the test, and the test passed. So I guess it's doing the right thing. So now we get to the point of more generic programming. So we've defined our own dual number type. I'm defining a new polynomial, and I'm plotting this high fidelity graph here where it's not entirely perfect right now, but I did the same here in the terminal, and there it's much better. So it's a text-based graph, and I can see that there's four real roots of this polynomial, somewhere between 0 and 5. and I might want to actually to find those exact roots. So I've written a simple Newton method, which takes a function f and an initial guess, and it does like a fixed number of iterations of Newton. Usually just a handful of them is enough to converge. And in every iteration, I'm computing f of x as well as its derivative in x. And then I'm doing the standard Newton update x. You subtract like f of x minus divided by the derivative of f and x. And now I'm giving it 4 starting points. So somewhere here at 1, 2, 3, and 4. And I'm applying the Newton method given this polynomial, this guy. And I want it to be evaluated, like I want to run the Newton method for all these different starting points. And I picked those starting points carefully, and it converges to all 4 roots. And I can actually verify that if I apply a polynomial to the roots, that it actually are roots. And or I could maybe also write it like this. Oops. And it evaluates poly in all the roots, and it gives me zeros, which is nice. So we have like this generic Newton implementation. And now one of the questions would be like, can we do even more with this? And there was this nice package that was released during the Christmas holidays of last year. And what it basically does is it, oops, I'm zooming in a little bit. What it basically does is it has a special number type. It's still fixed precision, but it gives you higher precision than just double precision. And the trick it does is it basically stores n of these floating point numbers, a fixed number n. And it's like an unevaluated sum in a sense. So let me just show you by actually pulling in this package. So for instance, if we have a square root of 2, it will give me the double precision version. But this package gives me floating point 64 times 2, which gives me extended precision to work it out, as well as float 64 times 4, and it gives me even more precision. So it can be useful to verify computation to more precision and see if actually like how errors behave, for instance, in your algorithms. If I actually look at what a multi-float, this float 64 times 4, what a multi-float type is, it turns out it's these 4 numbers, and they're decreasing in precision, as you can see. So this is more or less this unevaluated sum. And you can see that this is like a property that the second number here is in the round of the previous number, the first number. So you can verify that here really quickly, that indeed epsilon is like the distance between this particular floating point number and the next one. And you can see that it's in fact larger than the value of the second limb of this guy. So then the interesting part would be like, can I apply the Newton method with my dual number type to find the roots of my polynomial in higher precision? And it turns out this just works. So, clearly I have to verify that it actually works. And indeed, I'm getting some high accuracy results. So just to reiterate, the Newton function was this 6-liner, or what is it, 5? I don't know. It doesn't know anything about differentiation except for that it calls this dual number lifting function that we did. Also, it doesn't know about the function that I'm actually passing. It's just a generic function f. It definitely doesn't know about multi-float numbers, but just composing this, it just works, which is kind of neat. And then one of the questions you might have is like, okay, that's nice and all that it works, but what's the performance? And here I had to make a couple changes to improve the situation a little bit. So I basically redefined a couple of these functions that I implemented for like a basic arithmetic, as well as my polynomial and that lifting thing. And I'm wrapping it in like I'm writing it as a function now where I'm annotating it with the inline macro, which will tell the compiler that it should try hard to inline those functions. Then I defined this function getRoots, which basically just calls the Newton method on this particular polynomial defined earlier in the point x. And I'm also going to say it has to do n iterations, where the number of iterations is now a compile time value, because I'm wrapping it in the type itself. Val is some kind of a wrapper to hold like some value to make it a compile time constant. So basically this function gets specialized on the value of n2. And then, so just to get started, I'm running this code native macro again on the function getRoots, and with the starting point or the initial guess 1.0, and I'm doing 4 iterations of this. So this is the constructor for that guy there, for that type. And if I'm looking at the generated code, it's just a bunch of arithmetic. And for those who are well versed in looking at assembly code, you don't see a jump, meaning that the compiler unrolls the Newton. So it unrolled this loop. So that's kind of neat. Now the question is, what actually happens in the case of like this float 64 times 2, so in this multi-float thing. And again, it specializes on these types. And this time there is a label. And there's a lot of stuff happening, but then here there's a jump back, so it did not unroll the loop. Oh, I thought it would actually inline everything. There is one call to a function. I have to figure out what that is about, but otherwise things are mostly inlined, I guess, and there are fancy instructions, fuse, multiply, add, and whatnot. Then how about like factorizing this thing by hand? Like if I want to, if you remember, I started with 4 roots that I wanted to find. So why can't I do this just with like SIMD operations? Because it happens to be so that 4 numbers fit exactly in one register. Like 4 doubles fit in one register at the machine we're on bits Daint. So there is this package called factorization base, and I really like it. It's a very interactive way to do factorization by hand. And this is, for instance, a constructor. I'm giving it 4 numbers, and out I get this fac thing. It has length 4, and it stores 4 float 64s. So that's kind of neat. And then I might want to run Newton again on my polynomial function with the vector now as the starting point. And it works too. And I might to verify the results and evaluate. So the output here is, again, like one SIMD register in a sense. I might evaluate poly in this guy, and indeed it has found roots. You might even, VEC is not really exactly registers, it's more like a, so like a high level view of like machine registers. It's more like, well, you can see for yourself, if I'm passing 8 numbers, which doesn't make sense on bits Daint because it can only sustain 4 doubles per register, I'm actually getting something which is like 2 registers that's represented like this. And I can actually also run the Newton method on this thing with 2 registers at the same time. And it's kind of like a loop unrolling by hand if you're into that kind of stuff. And then you might actually want to see like what's the assembly generated by this loop unrolling thing. And again, I'm doing 4 iterations. calling the get_roots function again, starting with like one register. And it's all very pretty. And the thing that changed is there's YMM here. So it's using the 256 bits registers, if you're aware of these things. And it replaced this like factorized addition with backed doubles, and meaning that it factorizes actually. And it's very short, so it enrolled the loop, and it's nice. Clearly, not everybody wants to be looking at assembly code all day, and it's not really a useful way to actually know the performance of your functions that you define. So instead, you might want to look at this really cool package called benchmark tools. And basically what you can do is it exports this benchmark macro, and you just call your function as you would normally. So get roots, give it the initial guess, specify the number of iterations, and then set it up with the actual values like here. And you can run it. And as you can see, it takes a while because it evaluates this thing multiple times and does like warm-up loops and everything. So it ran it 10,000 times. And you can do all kinds of nice micro benchmarking here. And it gives you 11 microseconds. Well, then you might want to see, so how is the performance with the float 64 times 2? Turns out it's, okay, maybe I should not have rerun this. It's quite a bit slower, but like a factor, what is it, 10 or 11, 12 times slower. But it's still reasonably fast. More about this later, by the way, so we can better understand this. And the factorized, oh shit, now I'm running it again. The factorized version, it's doing 4 times the amount of work. It was actually giving me a bit of a slowdown. I don't know what that's about. I have to figure this one out. Maybe there's something, well, the previous time it ran, it was faster. Well, whatever, it's still faster than 4 times this guy. So it's like doing parallelization, but within registers. So basically, this example shows how to do like very high-level programming with dual numbers that we defined ourselves and putting in external packages for multiprecision. And it shows composability of like algorithms that are kind of unaware of all these types. And one of the things that you might think right now is that, okay, so probably you could also implement all kinds of trigonometry and special functions in Julia. And this is in fact something that people have done already. So for instance, if you use this which macro and use sine of 1.0, it will show you that it is implemented here in Julia. You can click on it. It will give you the code for it. And well, here you can figure out how the sine function works.
We need a bigger, oh yeah, there you go.
Yeah.
Perfect.
Well, it doesn't really matter. I mean, it's the point being that many of these otherwise low-level things that you would find in libm, for instance, on the system, are quite often implemented in Julia itself. Okay, so that's for the introduction. Let's see, we're at 3 right now. Before we go to GPU coding, I might have, well, this might be the point where you would also might want to have like a brief break. And it's certainly fine if you would go and fetch a drink right now. In the meantime, I think we can maybe also look at this shorter notebook that is still CPU programming, and it's more like micro benchmarking stuff. If you're interested in this, you can follow, and otherwise just take a break of 5 or 10 minutes. It's up to you. Let me see if this guy actually, if I have to restart the kernel here too. So I think I have to a couple of these things got cancelled. So so let me shut down the kernel, close the notebook, open this thing up again, and just run all the cells. So this is was a bit of a side project of me that I was interested in a while ago. I think it was also during Christmas holidays, actually, but a year before the multi-floats thing. It's the sieve of Eratosthenes, and it's like the standard way to compute or to find prime numbers is like this very old method, this prime sieve. And there are some interesting ideas that it's very easy to implement this algorithm, but to implement it in an efficient way is actually quite difficult. And I think the number one prime sieve in the world right now in terms of performance is this project here on GitHub. It's well, it has a lot of documentation. It's very fast and easy to install, and it's a very niche thing, but it's kind of fun to try that one out. The basic algorithm is like this. You have a string of booleans. Basically, they're all true. They correspond to the integers, positive integers, and you loop over them. And as soon as I get, for instance, to 2, I notice it's a prime, and I'm going to cross off all the multiples of 2, like 4, 6, 8, like this. And then I go to the next number. It's a prime number 3, and I'm going to cross off the multiples of those, etc. It's a very simple algorithm. Doing this efficiently is quite hard. Part of it is that it's if you do it naively, it's entirely memory bound. So this prime sieve project on GitHub, it does all kinds of tricks. It skips the 2, 3, and 5 multiples. It does something to make things cache efficient, and it has some crazy ingenious codes to unroll the inner sieving loop, as they call it. So let me just show you. It's horrible to look at. For those who are, well, let me just point out this. Every for loop here is entirely different. There is random numbers or seemingly random numbers. So for instance, this 19 here is not the same as the 17 there. There are 6 and 4s and bit 6, and here are all kinds of magic numbers. It's quite something. And it turns out that if you look at this, it's probably easier to write the code that generates all these numbers and things. It's probably easier to write the code that generates the code than actually to write the code that you saw on the web page. It is actually run. I think it did not. Okay, so one of my projects was to actually try and rewrite this in Julia. Okay, so I should have run this earlier because the naive version that I wrote here, it's very slow. So let's give it a moment. What I tried to do was actually write this in Julia, where, and this is a very neat feature about Julia. Sometimes it's easier to write code that generates code, and that's exactly what you can do in Julia. So my code, whoops, I have to. It's a macro in Julia, and you don't see, well, there's still magic numbers, a couple of them, but way fewer. A lot of it is devoted to documenting this so that I would not forget how it works. Yet I still am reading this again. I don't know how it works again. But it's a few hundred lines instead of 300. And there's a lot of Julia magic to make this possible. So let's see. Okay, so the naive version, this is like the sieve Eratosthenes where I'm allocating n booleans, and then it's this double loop crossing off composites and then returning the count to get like the number count. This will take literally 1.5 minutes to, and I should not have rerun this. So it takes 1.5 minutes to compute the total number of primes below 10 to the power 10. But if you import this package, it has a faster way of doing this, and it exports this function count primes, and apparently, there it is, 90 seconds. So now it takes a little bit because it has to compile everything, but it's reasonably fast. It's at 3 seconds, but this is still single-threaded Julia code. Then here I wrote this snippet to get the prime sieve code from this project. It goes to my Scratch directory. It clones the repository. It checks out the latest version and then builds the whole thing. And let's see if it actually does its job. It's building it. And then I can create this command and run it in Julia. So if you run it, it's like around at 0.2 seconds, which is quite a bit faster than my 2.9 seconds. But clearly, we are not using all cores, so why not try the parallel version? And okay, I have to admit, I'm still not there. Another 0.2 seconds, but I'm at 0.3. The thing is that it was quite a bit easier to just write the code that generates the code instead of having to handwrite it. And in fact, if you again use a code native macro and import a small sieve, you can do this for yourself. You will find what they call the highly optimized inner loop. That's in the documentation of this person's work. This is the highly optimized inner loop. And if you run code native on this small sieve function, in fact, you get the same, but it's using this extremely high level code generating code. So that's a very interesting aspect of Julia. I'm not like, I don't, this wasn't meant as assuming that you would exactly follow all the details in the few seconds I showed this Julia code, but I guess the point is clear. Okay, so we're about an hour in, and would be nice to slowly go towards GPU programming. And the idea would still be, once we get to GPU programming, that this kernel is like there, is it? Let's see. Let's evaluate 1 + 1. Okay, it also has to be restarted. Also in GPU programming, you can do a lot of very generic programming, which is kind of neat. Because often people say that GPU programming is difficult, and writing your own kernels can be a tedious task. But in Julia, I think you can do it from a notebook, and you can get good performance, and that's something we're gonna work towards too. So let me just run all cells and hope that it works. So I'm moving to this notebook, running the package manager to for those of you at home who might have to run activate first to activate the project in this folder. Let me just close it one more time. Sorry. Run all cells. Okay, so finally it's doing something. Instantiate might take a little bit of time because it's touching the file system. But let me just get started already. So Julia came with this linear algebra standard library, and it comes with bindings to BLAS. By default, it ships OpenBLAS, and OpenBLAS is not always fast. And in particular, so this is, I'm setting the number of threads to 1. On a single thread, it's doing quite decently. So it's peak flops function does some matrix multiplication and does some timings for it. It's computing all the things that are down here. So let me continue. Clearly, you don't want to do single-threaded computation, so you might be a bit interested into the specific architecture. So here is if I run ls topo, it'll show me all the details about the machine. And in particular, there are 12 cores that I might want to use, and they all have their own caches and a shared L3 cache and whatever. So if you know those details about the machine, well, the most important thing is just to use the right number of cores. I guess 12, not 24. So let's run this guy again. So if I'm setting the number of threads to 12 and trying to compute the number or get the peak flops of this machine, are we still computing? Okay, apparently it takes a bit. The point being that OpenBlast is not particularly fast. It gets you to like 400 out of the 500 gigaflops on a single node, which is not great. And it doesn't just, the threading bit in OpenBlast doesn't scale really well. So what you might want to do is to actually compare maybe different Blast implementations. And one way of doing so is to install MKL or Bliss, and it turns out that those are available through the Binary Builder project, which is a Julia project where they ship binaries of software cross-compiled for many platforms. But more interestingly, it would be kind of interesting if we could write like a simple CPU matrix multiplication, like a textbook version of it, and see what kind of performance we can get out of that. And as a side note, and this might be interesting for some people, in Julia 1.7, it will be using libblast trampoline, which is a C library that wraps Blast and dispatches to MKL or Bliss or OpenBlast, whatever, in a light. It's a light wrapper, and it can be used in other, like outside of Julia too. Another last note before continuing, you might want to set Julia num threads equal to 12 before actually running the notebook in your Jupyter hub and file, so that you get actually threaded Julia code instead of just threaded Blast. And you can verify that you're actually using a bunch of these threads by calling the number of threads function. I don't know why this is there something?
Maybe you check at the bottom of your notebook to see which cells it's getting blocked at. It looks like it's getting blocked because you did run all cells. So
yeah, but it was already.
Those ones are still waiting. So
I'm just gonna.
One of the bottom ones will still be running.
Yeah. Okay. I'll just continue maybe with the things that have already evaluated. Or let me just to be sure, let me shut down this kernel. Yeah, for the sake of time, we probably should continue. I pulled in this Blast benchmarks CPU package, and it turns out to have a convenient function that calls into MKL when I call it with some matrices, as well as setting the number of threads for MKL. And if I set the number of threads to 12, and I define my own peak gflops function, which takes like 3 matrices and computes a time elapsed to compute the matrix multiplication, returns the number of gigaflops. It'll give me, okay, on the first run, it gives me 445, which is close to 500. But you might also, if you rerun it, there might be some latency due to Julia compilation. Second time, it might be closer to 500. And let's also compare it to like a handwritten version using the loop factorization package that comes with Julia. It's a third-party package written by an individual. And it does actually a very, very good job at optimizing loops, sometimes better than the compiler actually does. It's entirely written in Julia. And for the user, it's extremely simple. You just add this little macro to your loop, and that should be enough to get started. Here you can see the kind of textbook version of a triple loop matrix multiplication. And one of the things we might start doing is actually to verify that that all these results are the same. So if I'm using my version of matrix multiplication, or if I'm using MKL, it is roughly the same as this version, which uses OpenBlast by default. And these tests pass, so we're doing the same thing. Then next thing I did was I created this function for for benchmarking small matrix multiplication. And well, small matrix multiplication are actually the only interesting thing to benchmark on the CPU, because clearly the GPU will be much, much better at the larger sizes. So I'm giving it a matrix size as well as the number type as parameters. And I added here the theoretical peak flops on this particular machine. So it's about 500 gigaflops. And I'm creating 3 matrices, and I'm also allocating them on the device using the CUDA package. And then I'm running these 3 benchmarks, Julia versus MKL and CUDA for this size M matrix. And I'm computing the peak, like the percentage of the peak performance, the Julia versus these other 2 guys. And then I'm using the bar plot that we've seen before to actually visualize the results. So starting with a very small matrix, like 32 by 32, it turns out Julia's, so just to reiterate, the Julia version of it is this tiny one with the magical macro here. The Julia version is actually really, really fast. And it turns out that this loop factorization, although it doesn't even know it's a matrix multiplication, is doing a really decent job at using very, very fancy SIMD instructions like masked operations and proper unrolling, all depending on the particular architecture that you're on at the moment. And it turns out to beat MKL and clearly cuBLAST because, well, at that size, you don't want to use CUDA. For larger, like increasingly larger sizes, you might want to plot what is happening. And it seems as if MKL is catching up on the size 65 or 65, but then it's just one off, and it turns out Julia's performance is increasing for about roughly 100 by 100. And in the meantime, the CUDA train is marching forward and soon takes over. But clearly, it shows one interesting idea in Julia, that there have been multiple attempts to write a BLAST library in Julia. But the outcome at this point, after so many years, is there is some generic macro that can be applied to any loop, and it will generate really good code for you. So that's kind of a neat feature. So then clearly, as soon as you go to the larger matrices and everything, you want to switch to using CUDA only. And what I'm going to start with is, these are not evaluated, so I might have to restart this guy here. So I'm going to evaluate these 2 guys. maybe this guy too. But let me already go to the stuff that's interesting. So if you would want to write a kernel in Julia that runs on the GPU, you can basically use the same, almost the same syntax. It's just you write an ordinary function, and I wrote a horrible kernel here that just tries to squeeze the performance out of a GPU just to see how close we can get to peak performance. This is a kernel. I haven't added any types here, but it takes a bunch of matrices, and then it computes an index to index into these arrays. I have to check, like, is my current thread in bounds? Is it not going out of bounds because a bunch of threads gets spun up? Then I'm indexing into my array to get some values from memory, and then I'm doing a loop. And in this loop, I'm doing 33 FMA instructions. So that's like A times B plus C, basically. And GPUs are quite good at doing FMAs. And then I'm overwriting these values again at the end of the inner, like the loop body. And after the loop, I'm writing them back to memory. Let's see if this has to work now. Okay, so it's evaluating. That's a good thing. Then here I have a CUDA peak flops function written myself. It's adapted from somebody else's work, but it takes a type, like a double precision. It takes a matrix order, like a size of a matrix. And then it either directly generates random numbers on the device, or if we don't have a float 64, it might generate random numbers on the host and then transfer them to the device. Then I'm calling this, or creating this kernel, the 201 FMAs kernel. Not launching it just yet. Get some configuration according to NVIDIA, what's the number of threads and blocks that make sense. I run the kernel just once to make sure that the machine is warmed up, or the device is warmed up. And then I'm using this elapsed macro to see how much time it takes to run this kernel. The kernel is run asynchronously, and the elapsed macro also adds a synchronize at the end, so that we're measuring the right thing. Otherwise, if you would just use a timer here, it would be instant. Then one FMA is like 2 floating point operations. So and returning the number of gigaflops. So running this, I'm getting at this point, so around 3,500. I believe the peak flops is 4,000. Maybe somebody can correct me, for double precision, and similarly for like single precision, I'm getting 6,000, which is kind of worse. It should be like, if it would be double, it would be 7,000. We might also compare this actually with cuBLAS, see what they can do, and probably they can do slightly better. So it runs maybe twice, and they get very, very close to 4,000 gigaflops. And for float 32, okay, they also get some number. So now, if you're doing GPU programming, you might want to be interested in, so okay, what is it actually? What was it actually doing? Because I wrote my kernel here, and it's just some code, but what is it actually turning into? And very conveniently, there is this macro device code PTX that will just dump out all the PTX code of the kernels that you're running. So for instance, if I run this here, it'll give me back this. It shows that this is the PTX for this particular kernel with these particular arguments or argument types. For this particular hardware, or like a generation of NVIDIA GPUs. And somewhere down here, we see a bunch of FMAs. And in fact, it's a loop because there's a jump to there. So it's reiterating this or iterating this thing a bunch of times. And you can see a -3, which is like the loop counter. So it apparently unrolled the loop 3 times because here are 18 instructions instead of what we had all the way up there, 6 of them. So that's kind of interesting. If we compare the performance between these guys, it turns out the 32 floating point performance was not exactly twice the number. So it's not 7,000. So you might want to be interested. So what's happening there? I believe I have that down here. Yeah. And it turns out it's much shorter. This is almost the same, but it's much shorter. And it just has 6 FMAs. So it's not unrolling. And that might be the cause of the slowdown. So clearly it's very, just stepping back a little bit, it's quite easy to get started with writing your own CUDA kernels. And also it's quite easy to get like a sense of what's happening even in a Jupyter notebook, which is kind of a neat thing. Going forward, if you remember those multifloats, it would be interesting to see if we can actually use them inside of our kernel. And I mean, because why not? Going all the way up. Oops, a bit too far. There are no type restrictions here. It's just some arithmetic. So why wouldn't it work? I made the CUDA peak flops to be giving, like it can be any type. So let's see what happens if we just plug in the multifloat. So I'm going to use this package. Turns out they don't have FMA implemented. There's no fuse multiply addition for multifloat. So why not implement it and do the stupid thing where we just it takes 3 numbers and we just do x times y plus z. Because we're good, nice people, we add a test and FMA with double precision. It turns out to be 2 times 3 plus 4 turns out to be 10. The test passes, so I guess it's doing the right thing. And then let's just run the CUDA peak flops thing that generates the kernel with our new number type. See if it actually works. There's a bit of a spoiler here, but actually, let's see if it works in the demo too. And it seems to do its thing. So I'm getting like 124. So these are not flops anymore. These are not gigaflops. This is more like giga multi-float doubles operations. And then one question you might have is like, is it actually performing well? And so basically we would have to count the number of floating point operations per multifloat FMA. And well, instead of going into the source code and see what the multifloat package actually does, you can also use, of course, another package to count them for you. And I actually have done that here. So in another notebook, I'm using the multifloats package. As I said, it, or maybe I didn't say it, but multifloat, the package also generates code for various levels of precision without writing all these tedious things by hand. So you can verify that here. You can plug in a 2 or a 4 and then see what happens. So let me activate this here. I have to rerun the kernel. Let's just skip over it. I already ran it before. So there is this package called gigaflops, and it does some magic, Julia magic, that lets you that temporarily overloads certain very low-level functions and allows you to wrap them. And what it overloads is like addition, subtraction, multiplication, division of floating point numbers within the context of this thing. So I'm computing 1 times 2 plus 3, which is like an FMA of float 64 times n, where n goes from 2 to 8. So it's all the supported multi-precision types by default. And then I'm just dumping the table, and you can see that it turns out if you do like in double precision, if you do a multiplication and an addition, it does 1 FMA operation, 13 additions, 18 subtractions, and 3 multiplications in double precision. So one double flop is in fact 36 double flop. So that's, well, you can go further and see how many flops are necessary if you increase the precision more and more and more. And you might actually want to fit a polynomial through them. And turns out that if you want increased precision, it comes at quite a cost. But well, it at least for double precision, it can be very useful to actually verify like convergence issues or check convergence issues in your algorithms and such on the GPU. All right. So 36 flop is 1. It's very difficult to float 64 times 2. 1 FMA is 36 flop. We counted it as 2, so we have to divide by 2 and multiply with 36. And it turns out our kernel seems to get at 62% of GPU peak performance without getting really into the hairy details of optimizing the kernel. Anyway, it's just generic programming, and it gets you quite far. Oh, actually, we got this was in my previous run. Maybe we get a little bit less this time, 62%. Oh no, that's not still not correct. Okay. It's okay, but it can probably be improved if you go into the details. And lastly, some things just work out of the box already. And this is more like high-level GPU programming already. So here I'm creating a random matrix where the element type is float 64 times 8, so still from the multi-floats package, size 100 by 100. And I'm just running A times B to do a matrix multiplication. And it turns out it falls back to some generic implementation in Julia, and it just computes the product in high precision. So here on the left-hand side is the CPU version. On the right-hand side, I'm taking the same matrix, creating a Q-array out of it, doing the arithmetic on the computation on the GPU, pulling it back and checking the difference. And so now I'm getting a dense matrix, like a dense linear algebra that just happens to work without me doing anything. And I don't know if this has been done already, but well, maybe we might also want to see if it's performing anything in a decent way. So it is like 1,000 by 1,000 size float 64 with 8 times or roughly 8 times the precision a matrix, move to the GPU, and then I'm timing it. And turns out like the in-place version of it is taking like half a second. So I guess it's okay. I don't know if this has been done already, but I showed in the other other notebook that you multi-float generates the code for higher precision arithmetic. So one of the things you could do is generate the code for even higher floating point arithmetic, and it goes like this. And okay, so here I have a matrix of 10 times or roughly 10 times the precision. And well, I'll leave it as an exercise to you to try that out. I'm not sure if anybody has done it already, but you can see if you can do like a very high precision multiplication on the GPU. Okay, I'm gonna leave the low level bits of like creating their own kernels and such. I'm gonna leave it right here. And now I'm gonna go to like the more high level interface only. Let me just close a couple of these guys. And let me just run the cells and see if it actually does its thing. Clearly, you don't want to be writing all your kernels by hand unless it's really necessary. Many things don't require you to go into these details, and many of the like FFT, BLAS, and whatever you have are wrapped and and also like reducing arrays and like high level array programming operations. They should kind of work out of the box. So I created this tiny PDE solver, and I've been looking at it for a bit. One thing I like about Julia, maybe this is a bit too much, but you can get all these nice Unicode symbols like this guy, and write comments where you basically just write the LaTeX version of it, hit tab, and you get like this Unicode symbol for it, and it helps you to like for instance write maps really clearly, and you can also use the variables to well, instead of having to do like row 1, you can do like row, and it's sometimes it's useful. It's more a gimmick, of course. So back to the PDE, there is this simple PDE, but I made it a little bit non-trivial so it's U depends on like spatial coordinates and time, and this is like a Laplacian, but it's fractional. So the P is like a number between 0 and 1, which is like a bit of a non-standard thing. It's somewhere in a cube. Well, I don't know if this is the actual, well, let's just say it's in a cube. There are some boundary conditions, and we're going to discretize this guy, like discretized in time first, with some backward Euler time stepping scheme. Move some terms to one side of the equation and apply the fast Fourier transform on both sides. Solve it in the frequency domain, and then fast Fourier transform it back to the real real space. And so the time stepping function, what it takes is, so let's say it's already some solution at some point in time. It also takes a plan for a fast Fourier transform forward and a plan for a fast Fourier transform backward, as well as this parameter P, that is the fractional part of this whole thing. And the algorithm is quite simple. I'm gonna apply the forward fast Fourier transform. Then I have had a lot of struggle to get these coordinates right, and well, you have to believe me that this is correct. These are these xi's here. I'm going to make xi a vector in each dimension, and then reshape it so that's like a more of a three-dimensional array type, but it has a dimension 1 and like a size 1 and all these other, like it's a vector but along different axes in a sense. And then I'm using Julia's broadcasting magic to do like scalar operations. And this might this plays really well with different array types. So this is basically the short version of this step here. And lastly, I'm applying the inverse Fourier transform and then returning the results. So although I'm using different variables here and there, the fast Fourier transforms are in place, and also this is in place. It's just for my convenience that I can reason about it. There's this one thing, maybe to devise. I'm creating a temporary vector. And depending on what type of array I'm giving to the matrix, to the time stepper, I might want to allocate this guy on the CPU or on the GPU. And basically, because it's just a short vector, I'm always creating it on the host and then maybe wrapping it to the device, depending on whether U is on the device or not. So if it's on the device, it should be a Q vector. If it's not, just do nothing, or like I want to get this guy back. All right. Now, I'm afraid I have to kind of skip over the 3D volume plots, which was very nice. But unfortunately, I didn't get to work in Jupyter Hub just yet. So I have to consult Tim and Jean in particular to get like remote rendering working. For now, I can just show you what it looks like on my personal computer. And so let's just share my entire screen. Can you see my screen?
Yep.
Good. I created this like one step of one time step where I'm creating random numbers, I'm doing a time step, and I'm looking at the real part and then doing a volume plot. And you get all these kinds of pretty pictures, and using a Julia library called Mackie. It's entirely written in Julia too, and it's getting quite stable. I'd hoped I could already show it off in the notebook, but at this point in time, it should be possible to do it, but I just didn't get there just yet. So that's what the solution of our problem looks like after one time step. And then you might actually want to see like a performance comparison of these two, where you run it either on the CPU or on the GPU. So I'm setting up some parameters here. Problem size is 256 cubed. The number type, I'm just using complex numbers because the fast Fourier transform expects that apparently. This is the fractional whatever parameter, and I'm creating a random array, moving it towards the GPU. I'm planning the FFT stuff ahead of time because I don't want to make this part of the benchmark. The underscores are clearly for like device arrays or device plans or whatever. I'm also adding a test to see if the GPU version does the same thing as the CPU version. And basically the same code works for the CPU and GPU. You just have to switch out the array type. So this is the time stepper on the CPU. This is the time stepper on the GPU. I have to wrap it in array to download it back to the host, and then I can compare these two solutions on the host. I'm looking if the norm is smaller than some small number, and it tells me that the test passed. So that's good. Then I'm running it once more on the CPU and the GPU and looking at the timings. And now there's something funny going on because clearly, okay, the test pass, CPU and GPU version are like 180 times, like the GPU version is 180 times faster, which would result in maybe a nice publication if it were true, but clearly it's too much to wish for. You can only get a 10x speed up or something, at least that's the order. So we're now kind of hitting a quirk in Julia on the CPU. I've written this very pretty code, or at least I like it, where I'm using all the kinds of broadcasting operations. So this particular bit where I'm solving something in the Fourier space. This is a bit of an issue though, because these guys are all vectors. If I'm doing this operation here, the output is a temporary, incredibly big, three-dimensional, or incredibly big. I mean, it's like 256 cubed temporary array, which is not great. So Julia is not smart enough at this point, just using these broadcasting operators to use this entirely lazily and defer the computation to when you actually need it. If I would remove these brackets and wouldn't solve a fractional PDE, then things would be much more efficient. However, that's not all. One issue is that broadcasting is not threaded by default. And there's a bit of a debate, like should it be threaded by default or should it not? It's well, I think it's currently still evaluated if the default of Julia should be that everything is threaded or not. I would, in some way, I would think that it doesn't really make sense to add threads to everything in the Julia base library, but well, opinions are there. It's an ongoing debate. So these are two things that actually slow down the computation on the CPU. And then you think, well, we've seen this loop factorization package. Can we just like stick this macro to it? And it turns out it doesn't work either at this point because this package is not mature enough yet to understand complex numbers. But also that is a work in progress. So for now, you would probably have to rewrite your algorithm just a little bit, where you would actually write a handwritten loop, which is definitely not as pretty anymore. So, well, I'm not going to go over the details, but basically 3 loops for every dimension. The outer loop is threaded. The inner loop is SIMD, so hopefully get some speed ups there. And the indexing is marked as inbounds to make it fast. And this is just like the abstract array fallback for the CPU. And I'm also specializing this solving Fourier space functions on the Q array on the GPU. And it's basically doing the same thing it did before. And then I re-implement my time stepper function. I think I have to delete this. This is the proper one. My time stepper function, it still takes the same arguments. Let's evaluate that guy. I'm running it again, so it's more or less the same as before. And now things look better with the threaded implementation, but 33 times speed up on the GPU is still hard to swallow. It should be 3 times faster on the CPU too. So, well, what can we do? This time it turns out it's not entirely on Julia. It's rather an issue with how we use memory in the CPU. And so this is one of the closing remarks on this benchmark. If we look at our three-dimensional array and look at the strides of these, turns out along the 3rd dimension, there is a particular, like if we do the FFT along the 3rd dimension, our data access pattern is really, really off. And it results in cache thrashing. So this is more of a technical thing that you just have to know. It turns out that it's basically effectively you're just using like a tiny part of your CPU cache during the computation instead of the full cache. So the solution would be to add a little bit of padding to the arrays. So here I'm doing it just on the CPU, and I'm starting with the problem size 256 cubed again, but now I'm adding, let's say, I don't know, 4 numbers of padding. So I'm allocating a slightly bigger multidimensional array, and then I'm making a few into this and only look at the first n, like this cube of just like the in a corner with just the first n elements in every dimension. I'm creating a plan again, and clearly, if you're very sharp, then you notice that plan f of t also works on views of multidimensional arrays. So I'm running this again, and okay, it's a bit variable, but I think this one makes a lot of sense. So I'm kind of cherry picking a good result, but it's now showing there is a 20 times speed up on the GPU versus the CPU. And previously, so just the memory trick gave us at least quite an improvement, like a 30%. Apparently, Julia is not yet there on the CPU, but it's now in a reasonable range where the performance are like in the expected ranges. So I'm gonna end a high-level overview, like how to write a reasonably high-level algorithm and use it on both CPU and GPU. I'm gonna leave that here. And with that, I've also come to the end of the presentation. I had some more notebooks, but it's been quite a bit, and let's just leave it here and have like a little break, or maybe we can already start with questions if there are any.